In this lesson, we're going to be covering the pesticide example, which is the two-way fractional design, the Bologna example, which is the three-way, and then briefly talk about some extensions. So let's recall what our ANOVA test looks like. We're going to have our null, which is going to be the effect is equal to 0 versus our alternative, which is our effect not equal to 0. Again, our effects are the interactions, two-way, three-way, and our main effects. Our test statistic is going to be the MS of whatever effect we're looking at divided by the MSC, where our degrees of freedom are related to the degrees of freedom for that specific effect, and the second degree of freedom is the error. Our effects, again, are the main effects, two-way interaction, three-way interaction. When we test, we always start with our three-way, two-way, and then go to our main effects. We start with the highest order, and then we move our way down based on if things are significant or insignificant. So let's get to our pesticide example. Again, this was an experiment where we were trying to decide the effect of 4 pesticides and the variety of a citrus tree on fruit yield. Here's our data table from lesson 7A we saw here. Now what we have is we're taking the means. We have our variety mean, so averaging our response here. We have our pesticide treatment means, so we're averaging down. We also, in this table, we have our cell mean. So this 44 is coming from the average of these two. This 48 is coming from the average of here. And this 67 is the average from here. To help us see our sums of squares, which again, you won't have to compute by hand, we tend to sometimes make this table called a corrected two-way mean. So here's our two-way means. The corrected two-way means is simply this number minus this number to get this number. This number minus this number to get this number. And the reason why I output this is so that when you go to look at your sums of squares for your SS factor A, B, your tab, or your SST, it's easier to just look at this number and then square it versus looking at the subtraction. So that's typically why someone might do the corrected two-way means. What I'm going to move down to now is the ANOVA table. Our ANOVA table, again, we're going to look at our two-way interaction first, which is here and here. And then we see our p-value of 0.18. And so we're going to fail to reject our null and conclude that there's no significant interaction between the pesticide and the variety. Because there is no interaction, we can test both our main effects. We now are going to move to looking at our main effects. Boom, 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 boom. The reason we can look at both of these is because both of them are treatments and they are not blocking factors. If they were blocking factors, we wouldn't want to look at them because we wouldn't be interested in testing them. So for factor A, our pesticide, we get a F value of 17.56, a p-value less than 0.001. So we reject the null and conclude that there is significant pesticide effect. We'd also do the same thing for our variety. Note, because we said that there is a significant effect, we could now go and follow up doing a Tukey or Fisher multiple comparison to see which treatment levels have an effect, or we could also do a contrast if we have a specific comparison. What we're going to go do now is we're going to jump to software to show you how we got this ANOVA table. To create the ANOVA table in JMP for our pesticide, we go up here to Analyze, Fit Model. Our responses are Y. We're going to click on pesticide, shift down, and so we're going to highlight both pesticide and variety. We're then going to go to this macro down here, and we're going to click full factorial. And so it will do the main effects and the interaction for us. And then we're going to click run. Now, we've seen this screen before. We're going to scroll down. We're going to have our ANOVA table down here with our effects test. Again, if you want them MS for them, you go down here, column, mean squared. Boom. Now, if we want our interactions, we can slide over here by interaction plots. We go to the red arrow plot. Interaction plot, we can click pesticide, and we see we have variety on the X, pesticide as our trace variable. We can also get the other one, go back to plot, create interaction. Now we're going to choose variety, so pesticide variety. Now, this is a little bit different than the randomized complete block design, or the GRCBD, because here it doesn't have to be specific that the block, we don't have a block, so it's not specific to that color. If we want the main effects, we go here, we can click plot, or we can go here, plot. Another way you can do this, which if you want cleaner graphics, and I suggest if you do want cleaner graphics, we can get out of this analyze, we can create our estimated cell means here, and our estimated treatment means, go to graph builder, and then use those in this area, similar to what we've seen in a previous lesson. So in the Bologna example, we're now our Bologna example is now the three-way factorial design. Our goal here was to assess the effect of the flour, the blend percent, and the SPI on our Bologna texture. So here's our data. We have our three-way mean here, i.e. just the mean of the replicates crossed. We have our two-way means. I color-coded these, so hopefully you guys notice that they're not the same thing. So this would be the blend in the cognac flour, cell means, blend with SPI, cognac, and flour. Did the corrected two-way means. Again, how I got that was this number minus this number went here. Then I calculated the sums of squares. Again, you won't have to do that by hand. I got the three-way means. But what I'm interested in is the ANOVA table. Again, you don't have to do any of that by hand. It's always good sometimes to maybe have it on record, though. So with our ANOVA table, our first thing we want to look at is our three-way interaction term, which has a here and here for our R, which we can see our p-value is 0.31. So we're going to fail to reject our H0 and conclude that there is no significant interaction between all of these. So with testing our highest order, our 3, we now can move to looking at our two-way interactions, which would be here. Our two-way interactions, I'll highlight in pink, are all significant. Okay? And so we can't just jump straight into our main effects because we need to look at what's going on here. Now, a little intuition tells me that I don't expect any masking because our main effects are also significant. But before making that jump, we want to do some investigation. So our two-way interaction terms are significant, so we got to go into our look at our interaction plot. Here's an interaction plot I made in that you make in JMP. We have our blend. How we read this is blend here is our X. So here's blend with 0.5 and 1. Then on these two graphs, your blend is your trace. On this graph, flour is your X. So think about which part this is aligned with. Here, it's going to be your trace. Here's your X. For flour, this would be flour and flour on your X, but then your flour is your trace for these two. So by just, let's look here where our blend is on the X, and we want to see if blend is being masked by the others. And I can kind of see why we got a significant interaction, because they're not exactly parallel. But also, if we were to draw the main effects plot in our head, we would probably see something like that and probably see something like that. And so I would say that there's no masking for A, and then the test on the main effect of our blend or factor A would be meaningful. We can also go look at our other two. So if we look at our flour is now our X, because this is how we can tell by our masking, is by looking at our variable on the X. Here, if we were to draw the main effect, it would probably be something like this. Here we see a little bit of anti-directional, so it kind of makes sense on, again, why interaction was there. But I don't expect it to be too much, and I might say the main effects would be like that. So there's a little bit of a cross between B and C, but I don't think it's enough. Also, we can go now look at our factor CSP. And again, if we were to draw the main effects, they would look similar to these trends. And so overall, I don't think A is masked by any factors, so the test of main effects would be meaningful. And there's a little bit of crossing with our B and C, but based on our problem and all that, and what our research question is the difference at the crossing is super small. And so maybe we could do it through a test of contrasts. And I would say that the main effects of B and C are also meaningful. So up here we had our p-values. We're going to reject that it was significant. We looked at the two-way interaction. We deemed that it is okay to look at the main effects of A, B, and C because of the reasons we just talked about. We have our main effects down here, and all the p-values are less than 0.01. How we found that was going back to our ANOVA table and looking at the p-values. So we reject for every main effect, but the reason I put a question mark is because we also have to remember to add the disclaimer. That while we see this pattern for the main effects, we might not observe the exact same pattern for the individual. So what I mean by that is right here we have the main effect for our SP. And if we were to come up here, this trend might not hold true for our red line. And so we just have to add the disclaimer that, yes, while we're saying that there is a difference, that difference might not hold based on the level you're at. Caution, how to interpret the test's results of a lower order effect while the higher order effect is significant. So if the main effect is insignificant, but the AB interaction is significant, or another example would be the AB interaction is insignificant, but the ABC interaction is significant. You just got to be really careful because the interpretation of this lower order effect depends on the inclusion or not inclusion of this higher order interaction. So before proceeding on exploring three-way and extensions, let's move to software to see how we got the ANOVA table, how we got this interaction plot here, and how we got these main effects. On the example, we're going to follow a similar procedure that we showed in the pesticide. We're going to go to Analyze, Fit Model. We're going to go Texture is in our Y. Now we're going to go and highlight our A, B, and C. We're not including mixture. That was for when we did the complete randomized design. We're now going to do our factorial design. We're going to go to this macro, full factorial, and it's going to get us everything. We're going to click run. We're going to get our results. We're going to go down here. We don't need this parameter estimate. That will be talked about more later in regression. But we have our ANOVA and our effects test. I did notice something interesting, that if you don't get this ANOVA table right away, you can go to this red arrow. You can go to regression reports and you can click it on and off. I noticed something weird on my computer, that it happened with one time, but you can still get it. If you want we can scroll all the way over here and we can do our plots. So we can create separates and we can go crazy with our three-way interaction, but since in this problem our three-way interaction was insignificant, we can just go look at our two-way interaction plots, which is similar to how we did it in Pesticide, and look at it that way. Or something a little bit easier, you go up here, you go to factor profiling, and you can go to interaction plots, and it will get the same plot you got in the notes. And then you can get the main effects here, like that. Thus far, we only talked about exploring the two-way interactions. That's mostly because three-way interaction plots can sometimes get messy, and it's not really fun to look at. One alternative is to reduce to a two-way interaction, so we combine a treatment factors, and then we use the third one as the trace, as in this example. To help us look. But we didn't have an interaction, so I wasn't too worried about looking at that. But again, it's possible, it just gets messy. There are extensions to factorial designs, which we briefly mentioned in Lesson 7A, and it's called a fractional factorial treatment design. Pretty much what it is it takes a full factorial design, and then it gets half or various combinations. The advantage of this is, especially when you start having 4 treatments, 5 treatments, 6 treatments, is that we're only going to use like half of a 2 by 2 by 2 3-way full factorial design. And so it's going to help us reduce our number of experimental units, which could help us reduce our cost and our time and all that. Disadvantage is you start getting confounding effects. So maybe the effect of A is confounded with an interaction effect of BC. So while these are useful, we will not cover them in this class, but they do have some advantages. With that, you should be able to now complete your homework, which is due Saturday.